For this project, we decided to test the probabilities of winning in a game called Chuck-a-Luck. In this game, players choose an integer from 1 to 6, and then roll a die 3 times, and depending on how many times that integer shows up depends on how much they win. If it doesn't appear, they lose their money. If it appears once, they win the exact amount of money that they bet. If it appears twice, they win twice as much. If it appears 3 times, they win 3 times as much. So, and this project will determine the probabilities of winning all 3 amounts and how much the house wins on average. So in order to do that, we had to find the probability of 0, 1, 2, and 3 times of landing on the integer, we had to find out all possible outcomes and all possible outcomes within each category. So we drew a tree diagram and counted up all the instances of, and we just used the integer of 1 just for consistency's sake. And we counted up all the times of it landing on 1, 0 times, once, twice, and 3 times. And what we found was that there was around a 63% chance of losing money. There was a 23% chance of winning exactly the amount of money back, and a 12.5% chance of winning twice the amount of money back, and a 0.4% chance of winning 3 times as much money back. The mean was determined to be negative 0.1435, which is about 14 cents, which is what the house wins with every dollar that was bet. So for every dollar that one person bets, on average the house will win 14 cents. So it means in the long run, the house will win 14% of all bets placed on this game. The standard deviation was found to be 1.1795, which is pretty high, meaning there's a large deviation in how much the house could win, meaning a player could win 3 times as much. So if they placed a $25 bet, they could lose $25, or they could win $75, making their total $100. So there's a lot of deviation. Our group decided to play the actual Chuck-a-Luck game 40 times. So we rolled a single die 3 times, and that was one set of numbers, and we did that 3 times. And we used the same number 1 for consistency's sake. Each set was then placed into its respective category, so 0, 1, 2, or 3 times with the integer, and then that was repeated 40 times. The numbers in each category were added up and then all divided by 40 to determine the probabilities from the simulation. So we ended up having 23. The frequency table looked like we rolled it 0 times 23 times. We rolled it once 12 times. We rolled it twice 4 times, and we rolled it 3 1 time. These values were then used to find new probabilities, which were respectively 0.575, 0.3, 0.1, and 0.025. These were then used to find the mean, or how much the house made, which was then determined to be 0. So on average, the house made broke even on average, meaning it could go either way. The standard deviation was calculated and was found to be 0.5916, which is a lot less than the previous standard deviation, meaning that there was a lot less deviation, and it could still go either way because the house made 0 on average. Simulation was a little bit different than our theoretical values. That was probably because the sample size of our simulation wasn't big enough to truly get up to the scale of a theoretical yield. It was close, but not exact.